Look at the ocean's surface, and it appears steady, but digital thermal maps reveal a hidden, violent reality. The water is boiling. These intensity maps show the scale. Widespread thermal anomalies are now impacting every major ocean basin simultaneously. Scientists define these events as marine heat waves. For decades, the ocean has absorbed 90% of the excess heat from human activity, acting as the planet's primary thermal shock absorber. Water has a physical limit for energy storage. As we approach that limit, the ocean's ability to stabilize the global climate is breaking. Marine heat waves occupy a massive three-dimensional volume that extends far below the surface skin of the water. Persistent high-pressure systems trap heat at the surface, while currents drive those anomalies thousands of meters deep. These profiles show heat distributing, sometimes staying in the mix layer or reaching the ocean floor. Even when the surface cools, deep pockets survive for months. Through reemergence, hidden heat eventually surges back to the top, prolonging the event. Because the entire water column is compromised, marine organisms cannot simply dive deeper to escape the heat. They are trapped. High temperatures initiate a mechanical shift in the water column called stratification. This forms a thermal lid. Warm, buoyant surface water becomes permanently separated from the cold, nutrient-rich water at the bottom. Phytoplankton are the microscopic foundation of the marine food web. They cannot survive without the nutrients that the stratification blockade now holds out of reach. During what should be a peak spring bloom, this nutrient starvation can reduce phytoplankton biomass by 70%. Decaying biological matter consumes oxygen, creating low oxygen zones, while heat spikes the water's acidity. The 2014 Blob in the Gulf of Alaska is the definitive example of this quadruple threat event. Across the Northeast Pacific, the combination of hypoxia and acidification eradicated commercial fisheries and decimated marine mammal populations. The data from the Blob identifies these heat waves as catalysts for localized, multi-system extinction. To monitor these subsurface threats, researchers maintain a global network of autonomous Argo floats and gliders. Climate models use this data to track patterns like El Niño. This comparison shows a forecast from 1997 that accurately predicted the 1998 heat wave months in advance. However, the background temperature of the ocean is rising so fast that the statistical definition of extreme is disappearing. Mathematical projections suggest several ocean regions will soon enter a permanent marine heatwave state. Our historical datasets are breaking down because the ocean has permanently departed from its normal state. The global consequences of this departure lead directly back to the health of microscopic phytoplankton. Phytoplankton pull massive amounts of carbon from the atmosphere. When they die, that carbon is buried in the deep ocean, keeping it out of our air. As heat waves eradicate these populations, the ocean loses its capacity to scrub carbon from the atmosphere. This creates a feedback loop. Less carbon absorption leads to more atmospheric heat, which generates more intense marine heat waves. By stalling the ocean's biological engine, we lose the planet's primary cooling mechanism. We are dismantling the thermal shield keeping our climate habitable.